downstairs. That's why I have to compensate it with an omega here, omega n. But quantum mechanically, there's a little correction, and the correction comes because the p's, because the A plus and A minus don't commute, and that gave us an n plus 1/2. The 1/2 is called the ground state energy, or the vacuum. Well, if it was field theory, we would call it the vacuum energy. If it is a simple harmonic oscillator, we call it either the 0-point energy or the ground state energy. And it's really a consequence of the uncertainty principle that you can't have both P and X simultaneously being 0. And since the Hamiltonian involves P squared plus X squared, there's no way they can cancel each other. So there's always going to be a residual bit of ground state energy there. You don't lose very much if you just cross it out and forget it, because an additive constant in the energy of a system really doesn't change its equations of motion. So you can ignore it, but it is there for some purposes. All right, what I wanted to do was to show you. Is there anything else? Yeah, there's one other important point, that equation that went into showing that the A pluses and A minuses were raising and lowering operators. It was the commutation relations of the A plus and A minus. Dirac's rule: whenever you see two things, commute them. Right. Sometimes, of course, you get garbage, but the commutators are A minus with A plus just equal to 1. Had I not put the square roots of 2 omegas down there, the commutator would have been something a little messier. And so really the reason for dividing by square root of 2 omega here was to get rid of anything on the right-hand side, to divide it away. This commutation relation, together with the definition of n, tells you that n is quantized in integers, and the connection with the Hamiltonian is such that the Hamiltonian, or the energy levels, are these. Yeah. Yeah. Why it stops at 0? Oh, why 0 is included. Okay, we're going to yeah. Okay. What we're going to do is we're going to demonstrate explicitly what the ground state is, that there is a ground state, and we'll find the ground state by actually solving the Schrodinger equation. And we'll see that there definitely is a state with 0. So, what is a wave function? A wave function in this context, let's just put parallel to this very tricky and clever operator structure here. Let's write down the wave function description of the same thing. State vectors are replaced by wave functions, which are functions of position. If we're talking about energy eigenstates, we could label the wave functions with a little n down here, indicating which integer they correspond to. The ground state, for example, will be psi 0. Well, the first excited state would be psi 1, and so forth. So, state vectors become wave functions. Operators, x, the operator x becomes just multiplication by the coordinate x. I'm trying to remember to use capital letters for operators and lowercase letters for just numbers. Okay, the momentum is replaced by minus I d by just derivative with respect to x. again, there's an H bar in there if you want to keep track of H bars. Oh, if you do want to keep track of H bars, here's where it goes, right here. And that's the only place where you have to modify what I've done here. Yeah, I guess maybe also here we want to put an H bar down.